Hello, everyone. My name is Rob Peglar, and I'm the president of Advanced Computation and Storage, LLC. Absolutely delighted to be able to present one of the MVP Days sessions for you. In particular, a session on Storage Spaces Direct, enabling the next generation of hyperconverged infrastructure. We call it Hyperconverged 2.0. Let's review a little bit on Hyperconverged 1.0, the previous generation, which I think is a really good start, but there are some interesting aspects to Hyperconverged 1.0 that I do want to talk about. In particular, a little overview. HCI is all about combining computing, networking, storage into a server. Most of you are probably very familiar with that. And it came to be several years ago as an alternative architecture in an enterprise data center, or perhaps in addition to, with the typical 3-2-1 enterprise computing layer, networking layer, and storage layer as well. I think, again, most of us are very familiar with that. The 3-2-1 has been around now for well over a decade. So in order to enable workloads, you create virtual machines on the hyperconverged infrastructure. And then, of course, our friends at Microsoft with Hyper-V since 2016 have enabled HCI in, I think, a very strong way. Lots of enterprise capability, lots of feature function. You can read the slide just as well as I can. And all of these feature functions have been enabled, and then even more so in Windows Storage Spaces Direct, especially in the 2019 Server Edition. So HCI 1.0, again, been around for several years now. People are familiar with it, gaining popularity in the marketplace. So let's talk about some of the implementations. How would you put together, construct such an infrastructure? Well, most practitioners with Hyperconverged today are acquiring what I'd call a small to medium capability server. Nothing dramatic, a socket, but typically 2 sockets, a handful of cores, kind of mid-bin CPUs, and a relatively small collection of storage devices, typically SSD or a hybrid SSD along with rotating, along with a fair amount of RAM, but not overly so. So again, these small to medium servers, and then you cluster them together with the hyperconverged software. Now, in terms of infrastructure, a lot of these small servers might take up quite a bit of space in a rack, perhaps a full rack of servers, 22U servers in a full rack. And then, of course, the requisite networking required for such an infrastructure. So lots of ports, typically today 10 gig, sometimes 25 gig as well. And of course, multiple ports per server to ensure resiliency and redundancy. But the bottom line in Hyperconverged 1.0, at least as practiced to date, is really, and I'll be blunt here, kind of mediocre to poor application performance. After all, one is acquiring and constructing this type of infrastructure in order to run applications and get workloads done, but especially latency sensitive applications, databases in particular, Microsoft SQL Server, but lots of other applications as well who are sensitive to latency. They have tended to remain on the legacy 3-2-1 SAN deployments strictly for the purpose of getting much more work done per unit time than perhaps the collection of small to medium-sized servers and a hyperconverged 1.0 infrastructure could provide. So, of course, if there was a 1.0, there is a 2.0, and I'll spend a minute or two talking about the current state of the art. So 2.0 enables the same capability, except with a different infrastructure, in particular, fewer, denser, more powerful servers. That's a step beyond what the typical 1.0 infrastructure looks like. So fewer servers, but each server is much more powerful than before, typically with high bin sockets, lots of cores, fairly fast processors, a fair amount of RAM, actually up to what most people consider a large amount of RAM, perhaps a terabyte, maybe 2. But RAM, of course, is a bottleneck in lots of server infrastructure. Having more RAM is always a good thing, can be taken advantage of. And then the use of NVMe SSDs, which I'll get into here in a bit. And several dozen devices, maybe as high as 72 or even 144 per server to enable this rich storage density. So what's the result of this? Well, you have fewer rack U, of course. You're literally shrinking the physical size of the infrastructure. And a good benefit, at least in terms of cost, is that now I need fewer switch ports, fewer NICs in the servers. I still want resiliency and redundancy, so at least 2, maybe 4 ports per server. But since I have fewer servers now, I can get away with less networking infrastructure and take advantage of increased bandwidth, perhaps using 100 gig Ethernet, for example. So what this does, if you roll that all up in an HCI 2.0 environment, is really enable very good, great, outstanding application performance. And again, especially in the latency sensitive area, the storage density of these more powerful servers with HCI software, and in particular, Storage Spaces Direct and Windows Server 2019, which I'll get into in a bit, this really enables running significantly more application workload, not only per server, but also reducing the time to result, or reducing the latency of these applications. And as we know, a lot of applications today, especially in HCI environments, are really I/O bound. They depend too much on fetching data from disk, perhaps using a network to do so, rather than a dense, powerful server with lots of local devices. So the workloads now, even latency sensitive workloads, run really efficiently on these HCI 2.0 deployments. So wrapping up the HCI part of this, why is it better for workloads? Well, in 2 words, it's storage density. If I have a dense collection of storage devices, and in particular NVMe SSDs, this gives me great data density relatively close to the processors that are in a particular server, and then within a dense cluster with a high bandwidth networking in between them. So keeping literally hundreds of terabytes of data close to the processors really enables very significant improvements in application performance, and as well as keeping much more data in a smaller amount of rack space. So this is a good thing. So all of this, you know, waterfalls down. You get less load per device. You're striping more thinly. You're taking advantage of more devices at lower queue depths. You have less latency. This is all good for workloads and results, of course, in the traditional I/O metrics like IOPS and throughputs being enhanced. But I'm not terribly worried about that. What I am worried about is getting application workload done in the smallest amount of time or at the fastest rate, so I can put now more workload on these type of HCI 2.0 servers. And then with enhanced resiliency, because I have a great density of storage devices to choose from, this brings into play Windows Storage Spaces Direct intelligent allocation, and I'll talk about that a bit later on in the presentation. So now let's turn to the cost side of the equation. Everybody is worried about cost, and rightly so. It goes along with putting together infrastructure, especially for hyperconverged. So why is hyperconverged 2 better for cost? You'd think that buying bigger servers with more devices would tend to increase cost rather than decrease it. Well, not only on a workload basis, but actually the overall spend is decreased by acquiring and operating fewer, denser servers. I have a very good friend in the industry. His name is Howard Marks. He wrote a blog about this concept. I encourage you to follow the link, and you can always get it after the presentation as well. But he wrote a very good blog illustrating that with facts and figures, why fewer, denser servers tends to be much better total operating cost, TCO, than it does with more servers of a less powerful variety. And a big part of that is reducing the spend on networking. All the ports and NICs and cables, and all of you that have done infrastructure know that story very, very well. So saving money on networking and taking advantage really of the technology that's available today. In particular, high bin CPUs with a lot of cores, relatively high frequency, taking advantage of the fact that these more modern CPUs have more memory channels, so they're getting more work done per unit time. And then, even more importantly, they have lots of PCI Express lanes to take advantage of this good density within a given server for storage devices. And then, of course, at the end of the day, more data closer to the processor. So better processing overall. And then, cake and eat it too, maybe perhaps reduce the software licensing cost because you're using fewer sockets and cores, albeit more powerful ones, there is a potential to reduce licensing costs as well. Okay, I want to show you an example of a next generation server or HCI 2.0 platform that I believe has been very well thought out. This is a design done by Excelio, and it really takes advantage not only of the powerful processors that I mentioned before, but look at the density of devices, 72 devices per server node, enabled through the use of very intelligent use of PCI-Express fabric switching, all integrated into the server. And by the way, this was showed live, this particular platform with Storage Spaces Direct and Windows Server 2019 was demonstrated at Ignite in the HCI Showcase booth. A 4-node cluster, only 4U in size, so again, relatively dense, doesn't take up a lot of rack space, delivered over 4 million IOPS at very low latencies. So again, I don't want to go into too much detail about this, but this is the kind of design which again is kind of unlike a small ordinary server that really helps your workloads accelerate through, get more work done per unit time, really have great storage density with all this modular design incorporating dozens and dozens of NVMe SSDs. Here's another way to look at it. What is the value of having, say, instead of a garden variety server, having a platform like this that had 72 devices in the same space as other manufacturers have 24, for example. So why is that so much better? Well, again, two things. The ability to carry workload and deliver low latencies against that workload. So having a lot of devices like this does two things. It gives you lots and lots of bandwidth, of course. So taking advantage of the PCI-Express and the fabric design within it, and then very predictable latency. That turns out to be a big deal, especially in database environments, is not only low latency, but predictably low latency. Some folks call this the tail latency problem, right? 99th percentile IO. What variation of that is to the normal or 50th percentile, the mean and median IOs. So if you can keep that window relatively narrow between what an average IO does and what the 99th percentile or even 3 or 4 nines does, that's a big win in your workloads being much more predictable. And then again, smaller clusters of larger servers tends to decrease cost overall. You wouldn't think so, but it actually does. And again, taking advantage of the density of the technology, more SSDs per server node, and reducing licensing costs. So now, you don't have to be afraid to run these, high intensity storage, data intense workloads on HCI servers. Again, Server 2019 with Windows Storage Spaces Direct. So this is again, 5 years ago, this type of technology did not exist. So HCI 1.0 grew up in that older technology, and that's just fine. But HCI 2.0 take full advantage of what's offered, and again, reduce your costs at the same time. So let's segue into some specific information about Storage Spaces Direct, which is called intelligent allocation. That's actually a phrase I use for it. In the Microsoft parlance, it's called delimited allocation. Now, this is relatively new. It's first made available by Microsoft in the Insider Preview build 17093, and then ongoing, of course. It's worthy of noting that it's not available in Server 2016. Again, this is a new piece of capability that I think is a very important addition to Storage Spaces Direct for 2019. So with that, the setup is it's best used in a 6-server or larger cluster, but you could go down as low as 3 or 4. But 6 to 10, that's a fairly standard number, and it works. Turns out that 6 to 10 range works really well with the limited allocation. So let's talk about the normal form, if you like, or regular allocation. So regular allocation, again, the goal is to take a given volume that you create and divide it into slabs, if you like. So sections or shards of the volume, distribute those copies to enable as high resiliency as you can. So you can see the cute little diagram over there. I split it up into 3 copies divided into slabs. and then allocate to every server. So I've got 6 in the mix. It's really simple. This is a standard way to allocate. Each server gets the same amount of data. Each drive tends to be homogeneous on that, so same capacity drives. And good news is you can survive 2 concurrent failures during regular allocation. That's a good thing. But as we know, Murphy lives in your data center. So what happens if you get 3 concurrent failures using regular allocation? You wouldn't think this happens very often, and we sure hope it doesn't, but it does. It has been known to happen. And then as well, with servers and racks, people tend to congregate servers in specific racks and distribute them. So for example, if you lose a PDU in one rack and now 3 servers go away all at the same time, again, concurrent failure, what happens, and if you look at the cute little slab diagram at the bottom, the whole goal to maintain access to the volume is to have at least 1 surviving copy with all the slabs. Well, guess what? If you do regular allocation, that doesn't happen. So all 3 copies of that, the 3 mirrors, none of them have all the slabs on one of the remaining 3 servers. So guess what? You're in trouble because your volume is no longer accessible, even though you did a nice, clean, simple, regular allocation. So to solve that problem, Storage Spaces Direct in 2019 has the concept of delimited allocation. Another way to say it is intelligent allocation. So instead of letting the system choose servers to spread across, you pick a subset of the servers that are recognized by Storage Spaces Direct to hold content. And you have to have, of course, for a 3-way minimum mirror, you have to have a minimum of 3. So slabs are only allocated to the servers that you specify, not all of them. So this is why it's called delimited. So instead of slabbing it over 6 servers, they're allocated over 3 servers, only the ones you specify. Now, again, this is quite straightforward to do, but it is different. You get a different result than if you did regular allocation. So now, let's go back to our 3 concurrent failure scenario. What happens? So I've got, you would think now ordinarily, I've got the volume only across 3 servers instead of 6. Well, gee, isn't that going to be worse? And the answer is no. The way that allocation works is that in this case, in particular, if you lose server 135, which were the same set of servers you lost in the regular allocation scenario, using delimited, if I have the volume slabbed across servers 1, 2, 3, guess what? Server 2 has a living copy of all the slabs, so you meet the criteria, which is the key yes or no proposition here, that you have at least 1 surviving copy. In other words, all the slabs on a given node in the cluster. So guess what? Your volume is still good. You don't have to update your resume. You have survived a triple concurrent failure. And again, you don't think this happens a lot? Well, guess again, especially with a large server collection, you could have such a failure. And in fact, this has happened out in the field, exactly why delimited allocation was brought into Storage Spaces Direct. All right, so again, this sounds fairly counterintuitive that allocating only over 3 servers instead of 6. Now, I will say on the website for Storage Spaces Direct, there is a full explanation with a table, which actually is very, very helpful, that gives you these percentages of surviving certain types of failures. And it turns out that using delimited allocation, as opposed to regular allocation, you reduce the odds of having a failure of that by 95%. So 95 cases out of 100, if you do delimited allocation across servers, you can survive a 3-way failure relative to the failure rate that you would get just by kind of normal regular allocation. Now again, this is somewhat counterintuitive because I've only got 3 servers in play, but this actually helps greatly, and I'll show you a little diagram here a little later that might help explain it all. So you're taking advantage of the fact that at least 1 surviving server, right? And in this scenario before, 2 out of the 3 servers that I had with delimited allocation actually failed, but the 1 surviving server had all the slabs available. because of the delimited allocation technique. Now, there is one caveat, or actually I'll call it a best practice, that you should ensure that at least one drive to hold capacity, so one capacity drive, is spare in each of these servers. And I won't go into great detail about how to set up a spare in a volume, but those of you familiar with Storage Spaces Direct, there's nothing new about this. We've had spare drives in volumes for quite some time in Storage Spaces Direct, so you'll probably already know how to do that. But the whole idea is to be able to update the allocation after the failure scenario, and I'll walk you through how that works. So that's why it does that. So it's not magic, it's math. and quite frankly, this is why delimited allocation was added in as a feature in 2019. Again, with a particular build insider preview and above. So now let's circle back to our conversation about Hyperconverged 2.0. So if I have nodes or servers that have very dense storage, dozens of SSDs per node, this not only means I have lots of SSDs available, but now I can use delimited allocation to set up these volume sets and make sure that the data is slabbed across certain drives appropriately and certain servers as well. It gives me a lot more flexibility in terms of allocation, where the data resides, on what particular servers. Now I have, again, lots of drives to choose from in an HCI 2.0 server, like the one Celio that I showed you. And not only that, but much superior capacity per server. I mean, literally instances of 500 terabytes, half a petabyte per server node, which in turn reduces the stress greatly on the network. If you have to shovel I/O across the network just to get bits from node 1 to node 2, now your bottleneck typically becomes the network. And again, the whole point of running application workload efficiently is to eliminate the bottlenecks. A great way to do this is to put local devices very close to the processors, connect them with PCIe fabric, not just lanes, but fabric as well, so you can take advantage of all the lanes all at the same time. And this, again, really significantly improves application performance. And quite frankly, because you're removing the bottleneck of these applications being I/O bound in these dense configurations. So storage and I/O efficiency, those are the keys to running hyperconverged infrastructure very well when you're considering your workloads, right? And again, after all, you're buying these things for a reason. The reason is to get the workload done. So let's get it done more efficiently than we have in the past. So here's some PowerShell examples for delimited allocation. And again, a lot of this information is available on the Microsoft website, of course. It's very useful. Most of you, I'm sure, that are listening to this webcast understand PowerShell, so I'm not going to walk you through too much of it. But to allocate a regular volume, you can see the PowerShell above. Again, it's very straightforward. New volume with some parameters, the size, the name, and you're good. And then Storage Spaces Direct will choose the set of servers that it sees and slab the volume across those servers, again, in the example that we had before. Now, to do a delimited volume, again, the new technique, there's actually a couple of more steps, but again, they're very straightforward. The first thing you have to do is enumerate your servers. As you might imagine, because you're going to be choosing the servers on which to allocate across. So you can see, setting the servers variable by finding out what the storage scale units are out there. So this is a set of servers. That's what you get at the end of that. Then again, you're allocating a volume with straightforward new volume. Give it a name, give it a size, and then tell it what fault domains to use. And a fault domain is, again, the set of servers that you have chosen to do the delimited volume allocation across. So now, there's a very handy PS1 file that Microsoft has put together called Get Virtual Disk by Footprint by SSU. A rather long name, but it's a great script. And what you see is the result of running that. You get the name, the total footprint of it. So how much space? Remember, this is triple mirror. So 100 gig delimited allocated volume takes up 300 gig of space. You knew that. And then you can see clearly which servers that particular volume is allocated across, and then hence which servers are holding slabs for that volume. So that's the good way to check allocation. Now, how to change allocation? Let's say you did have a failure, you lost a server, which again equates to a fault domain. So I want to get rid of that server, take it out of the volume play, and then add a new one in. So the first thing you do is add the new one. So let's say you've picked a new server to bring into the volume. That's the PowerShell, how to do, add that. So you're getting the virtual disk on a particular volume, and you're adding a domain to it. And you can see with the $server sub3, that's the new server. I had it originally over servers 0, 1, and 2. Now I'm adding 3 into the volume. And then and only then, you can remove the first server from the volume, which is the one that has failed. So you're telling storage spaces direct, nope, take this one out of play. Don't consider it anymore for this particular volume. And then, very important step, is rebalancing the storage pool. Now, this is not a change. You would do this after any failure scenario anyway, and that's the PowerShell to rebalance the pool. And again, that's a wonderful command, a very useful and necessary feature to keep your workloads running optimally. Now, I won't go through, yes, there is math, even though you were told there would be no math, there is. I won't go through this, but this is the math behind it. It's combinations. You're picking servers and volumes. How many servers have? How many concurrent failures do you want to survive? You might want to survive 4 concurrent failures in an 8-server scenario, say. So you can do the math where, again, very straightforward elementary combinations, and see how many choices there are. As you add servers to the mix, you actually increase significantly the choices that you can have. So again, I'm not going to walk through all of this, but let's look at a pictorial of a perfect, to use a word, 6-volume example where I've got 6 volumes with delimited allocation across 6 servers, and you can see the servers, the numbers of the servers in the curly braces to the right. And again, this is how you, one volume at a time, this is how you build up delimited allocation and make sure that, again, this maximizes fault tolerance, this particular diagram. And you can see as you would add more servers, now you have more combinations to allocate. Maybe you're going to do 3- or 4-way mirroring. You get the picture, I think. So this is an example of perfect 6-volume example with delimited allocation. Very good. Well, that's what I have for you today. Again, thank you so much for allowing me to present on the webcast. You can see my email address there. Feel free to email me with questions. Again, my name is Rob Peglar, and I'm President of Advanced Computation and Storage. Have been delighted to present this webcast to you on behalf of MVPDays. So with that, I'll end. Thank you very much, and appreciate your listening.